Hello and welcome to UGC PG Pathshala. I am Anushri Nagpal from the Department of Geography, Jamia Millia Islamia. I am presenting this module on behalf of Dr. Suresh Kumar Banduni. In this module, we will learn about wastewater treatment, reclamation and utilization of low quality water. In this episode, we will learn about wastewater treatment, its reclamation and utilization of low quality water. Introduction. Wastewater is a liquid waste consisting of animal, vegetable, mineral or chemical matter in solution or in suspension with water. Its quality has been adversely affected by human impact. Wastewater can originate from a combination of domestic, industrial, commercial or agricultural activities, surface runoff or storm water, and is no longer considered fit for consumption. Wastewater includes water that is released from offices, households, industries, and retail buildings and manufacturing plants. It includes substances such as food wastes, chemicals, oils, soaps, fuels used in manufacturing units, etc. In homes, this includes water from kitchen and bathroom sinks, bathrooms, toilets, washing machine and dishwashers. Businesses and industries also contribute their share of used water. Groundwater can get contaminated and due to leakage from septic tank or agents such as insecticide, petroleum products, blood or cleaning liquids. Water quality. Water quality describes the condition of the water including chemical, physical and biological characteristics concerning suitability for drinking or swimming. It is measured by several factors such as the concentration of bacteria levels, dissolved oxygen, the amount of salt or the amount of material suspended in water. In some bodies of water, the concentration of microscopic algae and quantities of herbicide, pesticides, heavy metals and other contaminants may also be measured to determine water quality. Therefore, the scientific measurement of defining water quality does not necessarily mean that water is good or that water is bad. So, the determination is typically made relative to the purpose of the water, whether it is for drinking or to wash a car with or for some other purpose. What is in wastewater? Domestic wastewater is essentially the waste generated from homes and conveyed by means of water from the dwelling to the place of treatment and final disposal. The chief components of domestic wastes are body wastes like feces and urine, bathroom used water, kitchen wash water and laundry wastes. Industrial wastes pose a greater threat than domestic wastewater. They consist of discharges from various manufacturing, chemical, mining and other industries. The discharge from each and every industrial premise is governed by various legislation and permission to release of wastewater needs to be taken from the local authority concerned. Some industries produce waste which are unacceptable for sewer discharge and must be treated or disposed of separately. The discharge from industry is usually controlled by means of municipal rules and regulations. Certain discharges are prohibited in terms of these bylaws for discharge into the sewerage system and require some form of treatment, for example, co-disposal on landfill, pre-treatment, encapsulation or the use of evaporation pans. What is composition of wastewater? Wastewater is 99.99% water. The other 0.01% is of concern, which includes the following. First, nutrients. Phosphorus and nitrogen. Second, fats, oils, grease like used in cooking oils, body lotions, etc. Third, pathogens, disease causing bacteria and viruses. Fourth, BOD, biochemical oxygen demand. BOD is a measure of oxygen needed by aerobic bacteria to break down organic matter. A higher BOD means there is more organic matter that needs to be broken down. 5. Other solids. On analyzing the composition of water, it has been found that of the total solids, 50% of it is dissolved and rest 50% has suspended solids. Of the suspended solids, 50% will settle. The typical composition of wastewater is based on strength. Industrial activity changes the composition of wastewater often introducing toxic substances such as chromium and cadmium from planting operations. Where does the wastewater go? Wastewater drains into a network of pipes maintained by the local sewer services municipalities. Sewer systems are built to collect and flow wastewater and rainwater using the natural slope of land, generally towards the sea front or to wastewater treatment plants. Often, contaminated water can also be passed through the municipal filtration system and be prepared for use once again. However, the nature of the contaminants may require additional measures before the water is suitable for use once more. Wastewater treatment. Wastewater treatment is not a new concept. Wastewater were treated in ancient times by Greeks and Romans, as proved by the presence of historic sewer Cloaca Maxima built many centuries ago in Rome. Wastewater treatment is another way of utilizing water, as it is interconnected with the other uses of water. Nature has an ability to cope with small amounts of wastewater pollution. However, every day huge amount of wastewater and sewage is produced across the world, which needs to be treated before releasing it into the environment. Treatment plants reduce pollutants from the water to a certain level which can be handled by the nature. It reduces the contaminants to acceptable levels so as to be safe for discharge into the environment. Objectives of wastewater treatment. The major aim of treatment plants is to eliminate as much of the suspended solids, particulates, as possible before the remaining water is discharged back to the environment. As solid material decomposes, it uses up oxygen, which is needed by animals and plants living in the water. Many local authorities operate wastewater treatment plants that help to purify the sewage and recycle the water for other uses. The plants may employ many different devices to recycle the wastewater, including filters and chemical treatments. Fully functional water filtration plant is a priority for most municipalities. Cleansing and disinfecting the water reduces the chances of diseases outbreak related to infections and exposure to contaminants, making it possible for people to live in urbanized areas and still enjoy safe drinking water. The wastewater treatment plants were set up to minimize the adverse conditions caused by the release of raw effluents to water bodies. The water treatment is done to prevent destruction and contamination of natural water resources and water bodies. It includes chemical, physical and biological processes to remove chemical, physical and biological contaminants. Wastewater treatment involves two major steps. First, primary treatment, where gravity settling of solid particles is done. Second, secondary treatment is done by microbial transformation of organics and ammonia to reduce BOD. There are three levels of wastewater treatment. First, primary, second, secondary, third is tertiary. Primary, which is the mechanical method of treatment, this is normally the first stage of treatment of wastewater. It includes screening, grinding, flocculation or coagulation and sedimentation. It is designed to remove gross, suspended and floating solids from raw sewage. In screening, big size suspended materials such as rags, wooden pieces, wires, etc. are removed. Screening system consists of two units. The first unit, that is the coarse screen, consists of metal bars or heavy wires spaced 25 to 40 millimeters apart, and the second unit consists of fine screens. The materials removed by screening are usually incinerated. This level is sometimes referred to as a mechanical treatment, although chemicals are often used to accelerate the sedimentation process. Primary treatment can reduce the BOD of the incoming wastewater by 20 to 30% and the total suspended solids by some 50 to 60%. The grinding is carried out in grinders of rotating screens with cutting teeth. These are used to chop the solid materials to size smaller than 6 millimeters. Coagulation or flocculation. Chemical treatment precipitates the solids by coagulation or flocculation, and coagulates thus formed settle down rapidly. Coagulates are then removed either by sedimentation or by filtration. The important coagulants are ferric sulfate or aluminium sulfate with lime. Sedimentation removes 80 to 90% of settleable solids and reduces the strength of sewage by 30 to 35%. Sedimentation tanks are used to settle suspended solids. They may be primary or secondary. When a sedimentation tank is used for settling suspended solids before biological treatment, it is called primary sedimentation tank. When a sedimentation tank is used for settling suspended solids after biological treatment, it is called a secondary sedimentation tank. After sedimentation, solids left behind in the settling tank are piped to a sludge digester where the organic matter is decomposed in the absence of air. Secondary or biological treatment removes the dissolved organic matter that escapes primary treatment. This is done by bacteria consuming the raw matter as food and converting it to carbon dioxide, water, and energy for their own growth and reproduction. The biological process is then followed by additional settling tank to remove more of the suspended particles. About 85% of the suspended solids and BOD can be removed by a well-running plant with secondary treatment. Secondary treatment technologies include the basic activated sludge process, the variants of pond and constructed wetland systems, trickling filters and other forms of treatment which use biological activity to break down organic matter. It involves mainly the trickling filters, oxidation ponds and activated sludge process. First, secondary treatment involving the use of microorganisms to remove BOD of any solid that pass primary treatment. Oxygen is limited and must be supplied. The most common secondary treatment processes are activated sludge. Second, secondary sedimentation to remove microorganisms from secondary treatment. Third, disinfection to kill pathogens using chlorine. Purification by treatment on trickling filters depends primarily on absorption as well as adsorption of both soluble and suspended matter from the waste matter into and onto zoological slimes. They later develop and proliferate on the surface of the filtering medium over which the water trickles. As a result of flow of wastewater through the beds, decomposition takes place and soluble substances as well as sludge-forming solids are synthesized. Protozoa, fungi, bacteria, and other living organisms are responsible for these decomposition and oxidation processes. These bacteria decay their dissolved organic matter and absorb nutrients and energy. Any solid matter present is piped to a settling tank which is then transferred to a sludge digester where it is decomposed by microorganisms. Oxidation ponds. An artificial pond of shallow depth in which sewage is retained and biologically treated is called oxidation pond. The sewage in the oxidation pond is treated by the dual action of algae and aerobic bacteria. Sewage is controlled under climatic conditions which are favorable for the growth of algae, mainly sun, light and temperature. The aerobic bacteria get oxygen from the atmosphere and convert the organic matter present in the sewage to stable compounds by oxidation and liberate carbon dioxide. The carbon dioxide produced during the decomposition of sewage is utilized by algae for photosynthesis and liberate oxygen. The excess oxygen is used to keep the pond in aerobic condition. The detention period in the pond is 2 to 40 days. Oxidation ponds are efficient in removal of BOD and coliforms. BOD removal is about 90% and coliform removal is about 99%. Activated sludge process. Sludge or slush accumulates from primary, secondary and tertiary precipitates. Sludge volumes are reduced and disposed of as follows. Slow gravity thickening to remove excess water. Anaerobic digestion, also called as stabilization. Dewatering using a belt press or drying beds. Disposal for land application or landfill. In this process, biologically active sludge is continuously circulated through organic waste in the presence of oxygen. The activated sludge contains aerobic microorganisms which digest the raw sewage. Some activated sludge from the previous run is introduced into the raw sewage and provide sufficient aeration. Aeration activates the sludge particles so as to develop an active culture of aerobic organisms. In activated sludge process, sewage is first given primary treatment. Then the sludge is mixed with the sewage properly in presence of sufficient amount of oxygen. Bacteria present in the activated sludge multiplies rapidly, as a result of which solid organic matter present in the sewage are readily oxidized and suspended, as well as colloidal becomes clear. In addition to the aerobic oxidation ponds, anaerobic plants like septic tanks are also used to treat sewage like human excreta. A watertight single-story tank in which sewage is retained for long time to allow sedimentation is called a septic tank. In a septic tank, the anaerobic bacteria do the biochemical reaction and the settled sludge or slush undergo anaerobic digestion. During the detention period, the effluent is taken to soak pits for disposal and the sewage is purified. Tertiary treatment is simply additional treatment beyond secondary. Tertiary treatment can remove more than 99% of all the impurities from sewage, producing an effluent of almost drinking water quality. The related technology of tertiary treatment is time-consuming and expensive, which requires high level of technical know-how and well-trained treatment plant officials, a steady energy supply and chemicals and specific equipment which may not be readily available. An example of a typical tertiary treatment process is the modification of a conventional secondary treatment plant to remove additional phosphorus and nitrogen. The aim of tertiary treatment is additional purification of wastewater as well as its reuse. Tertiary treatment is the most advanced phase of sewage treatment, which is provided to only 2% of domestic sewage. The main function of tertiary treatment is to decrease the load of nitrogen and phosphorus compounds present in the effluents by the following processes. The effluent received after the secondary treatment is mixed with lime, that is calcium oxide. The lime reacts with phosphorus compounds in the waste to form insoluble calcium phosphate, which then settles down at the bottom of the settling tank, from where it can be filtered out. Nitrogen present in the wastewater is generally in the form of ammonia gas, nitrates and nitrites. The wastewater containing ammonia is directed into a metal tower. As water trickles downwards over a series of small plastic baffle plates, air is forced upwards through the effluents, which thereby results in the removal of ammonia gas. Chlorination before discharging the effluents, disinfection done with chlorine, can be the final step of wastewater treatment. Chlorination is done to kill disease-causing microorganisms that might be present in wastewater. Many advanced physic-chemical methods are used for treatment of wastewater, especially industrial wastewater, to remove inorganic compounds. These are adsorption. It is a mass transfer process by which a substance is transferred from the liquid phase to the surface of a solid and becomes bound by physical and or chemical interactions. By making use of active adsorbents, it is possible to purify completely the water from organic and inorganic impurities, even in very low concentrations. Finally, dispersed substances with a higher surface area such as sawdust, ash, peat, clay, etc. can be used as adsorbents. Activated carbon of various grades is the most efficient adsorbent. Ion exchange. In this, a reversible interchange of ions between the solid and liquid phases occurs, where an insoluble substance like resin removes ions from an electrolytic solution and releases other ions like charge in a chemically equivalent amount without any structural change in the resin. Ion exchange can also be used to get valuable heavy metals from the loaded resin by elution with suitable reagents. Electrodialysis. This is used for desalination of water, that is, for the removal of dissolved minerals, salts, acids, alkalis and also the radioactive substances from effluents. Electrodialysis is performed in a multi-chamber membrane apparatus known as electrodialyzer under the influence of electric current and used for separating the ions of inorganic compounds. Reverse osmosis. Reverse osmosis is a perfect tool that can reject particles as small as 10 raised to the power 3 to 10 raised to the power 4 nanometers. It is a pressure-driven membrane process in which water can pass through the membrane while the pollutant particles are retained. By applying a greater hydrostatic pressure than the osmotic pressure of the feeding solution, cationic compounds can be separated from water. Wastewater utilization. Importance of usage of wastewater. Water has become a limiting factor in all parts of the world. There should be proper and judicious use of water. Water resource planners are continually looking for additional sources of water to supplement the limited resources available to their region. In areas where availability of fresh water is less, whether in terms of rainfall or good quality underground water, source substitution appears to be the most suitable alternative to satisfy less restrictive uses, thus allowing high quality waters to be used for domestic supply. Low quality wastewater should, whenever possible, be considered as alternative source for less restrictive uses. Total 47 countries that engaged in reuse of wastewater, in which 12 engaged in reuse of untreated municipal effluents, 7 engaged in the reuse of both treated and untreated effluents, and 34 reuse wastewater only after treatment, and about 58% untreated or raw sewage water generally used for irrigation, mostly in China and Mexico. About 5.5 BGD of municipal treated wastewater is reused globally in 43 countries. The United States was first among them in the total volume of water reused. Many developing countries face the challenge of uneven distribution of clean water. Thus, water reuse should be considered as a viable option before water availability is matched by water demand. But water needs to be treated to potable standards before being reused to avoid any health disaster. The global problem of water shortage can be tackled with the effective utilization of water and reduction in wasteful consumption. Water can be reused by treating wastewater with the use of chemicals in order to remove harmful agents from the water and make it safe for further use. Types of wastewater use. Water gets recycled by natural systems but gets deteriorated by different levels of pollution. Once used, however, water can be reclaimed and used again for different beneficial uses by implementing wastewater reuse system. Direct reuse is deliberate use of treated wastewater for some purpose, including irrigated agriculture. It is also observed that people will drink wastewater from an indirect source unless proved unsafe to drink. People will not, however, drink water from a direct source unless tested or proven safe. Indirect reuse refers to water that is taken from a lake, aquifer or river and streams which has received sewage or sewage effluent. The reuse of wastewater for irrigation has been most successful near cities where wastewater is easily available and where there is a market for agricultural produce. The storage of treated wastewater may be necessary because supply may not match demand. Reuse of wastewater requires careful planning, adequate and suitable treatment, careful monitoring, appropriate legislation, and implementation of legislation and quality standards. The quality of the once used water and the specific type of reuse define the levels of subsequent treatment needed as well as the associated treatment costs. It is important to first consider type of water use, and efforts should then be made to be more economical in these sectors. Industry and agriculture though require large volumes of water, but not the quality need not always be high. Agricultural use as well as industrial use of water is very important as it is being used in voluminous quantities. Agriculture and aquaculture. Water is maximum used for agricultural purposes. Irrigated agriculture has a dominant role in sustainable crop production in years to come. On a worldwide basis, wastewater is the most widely used low-quality water, particularly for agriculture and aquaculture. Wastewater collected daily can be used to water smaller kitchen gardens. When this wastewater is used as a source of irrigation by the farmers, it reduces the need for fertilizers. There is an easy availability of wastewater in all seasons, especially in the lean season. The requirement of additional application of fertilizers has decreased with wastewater irrigation. There is a substantial increase in crop production to as much as 1.5 times as compared to the time when groundwater is used. Also, the quality of vegetables produced was up to the satisfaction level of the farmers. As a consequence to the above things mentioned, it has led to higher income generation with wastewater generation among the farmers. The farmers can save a lot in their monthly expenditure with the use of this water. In some homes, people sometimes take steps to recycle wastewater themselves. Water used for bathing may be collected and utilized for watering flower or vegetable gardens. The same is true with water used in the preparation of food. Any liquid used to boil pasta, for example, may be recycled as water for plants rather than dumping the used water into the sink. If wastewater is sometimes added to the compost pile, it will help it to rot down quicker. The voluminous amount of low-quality water used for agriculture involves the associated health risks and environmental concerns. Urban. In urban areas, reclaimed wastewater has been used mainly for non-potable applications such as irrigation of public parks, recreation centers, athletic fields, schoolyards and playing fields, and edges and central reservation of highways. Irrigation of landscaped areas surrounding public, residential, commercial and industrial buildings, irrigation of golf courses, ornamental landscapes and decorative water features such as fountains, reflecting pools and waterfalls. Fire protection, toilet and urinal flushing in commercial and industrial buildings. The disadvantages of urban non-potable reuse are usually related to the high costs involved in the construction of dual water distribution networks, operational difficulties, and the risk of cross-connection. Potable urban reuse can be performed directly or indirectly. Indirect potable reuse involves allowing the reclaimed water, or in many instances raw wastewater, to be retained and diluted in surface or groundwaters before it is collected and treated for human consumption. Direct potable reuse takes place when the effluent from a wastewater reclamation plant is connected to a drinking water distribution network. Treatment costs are very high because the water has to meet very stringent regulations which tend to be increasingly restrictive, both in terms of the number of variables to be monitored as well as in terms of tolerable contaminant limit. Industry. The most common uses of reclaimed water by industry are evaporative cooling water, particularly for power stations, boiler feed water, process water, irrigation of ground surrounding the industrial plant. The use of reclaimed wastewater by industry is a potentially large market. Industrial reuse of water is cost effective for industries where potable quality of water is not required, and where industries are located near urban centers where secondary effluents is readily available for reuse. Recreation and landscape enhancement. The use of reclaimed wastewater for recreation and landscape enhancement ranges from small fountains and landscaped areas to full water-based recreational sites for swimming, boating and fishing. As for the other types of reuse, the quality of the reclaimed water for recreational uses should be determined by the degree of body contact estimated for each use. In large impoundments, however, where aesthetic appearance is considered important, it may be necessary to control nutrients to avoid eutrophication. With decreasing water availability, low quality water is being increasingly used in agriculture. Its utilization provides new sources of water for higher food production in many areas, but its use could create environmental and health hazards. Environmental benefits from use of wastewater. Wastewater reuse has environmental benefits. The factors that may lead to the improvement of the environment when wastewater is used rather than being disposed of in other ways are avoiding the discharge of wastewater into surface waters, preserving groundwater resources in areas where overuse of these resources in agriculture are causing salt intrusion into the aquifers, the possibility of soil conservation by humus buildup and by the preservation of land erosion, the aesthetic improvement of urban conditions and recreational activities by means of irrigation and fertilization of green spaces such as gardens, parks and sports facilities. Negative environmental effects. Despite above discussed benefits of use of wastewater on environment, some potential negative environmental effects may arise in association with the use of wastewater. One negative impact is groundwater contamination. The main problem is associated with nitrate contamination of groundwaters that are used as a source of water supply. This may occur when a highly porous unsaturated layer above the aquifer allows the deeper percolation of nitrates in the wastewater. If there is a deep, homogeneous unsaturated layer above the aquifer capable of retaining nitrate, there is little chance of contamination. The uptake of nitrogen by crops may reduce the possibility of nitrate contamination of groundwater, but this depends on the rate of uptake by plants and the rate of wastewater application to the crops. Buildup of chemical contaminants in the soil is another potential negative effect. Depending on the characteristics of the wastewater, extended irrigation may lead to the buildup of organic and inorganic toxic compounds and increases in salinity within the unsaturated layer. To avoid this possibility, irrigation should only use wastewater of predominantly domestic origin. Adequate soil drainage is also of fundamental importance in minimizing soil salinization. Extended irrigation may create habitats for the development of disease vectors such as mosquitoes and snails. This can further lead to the problem of various vector-borne diseases like malaria, dengue, chikungunya, etc. To combat this, it is important that the integrated vector control techniques should be applied to avoid the transmission of vector-borne diseases. Indirect health-related benefits can occur because wastewater irrigation systems may contribute to increase food production and thus to improve health, quality of life and social conditions. However, potential negative health effects must be considered by public health authorities and by institutions managing wastewater reuse schemes because farmers, consumers of crops and to some extent nearby dwellers can be exposed to the risk of transmission of communicable diseases. Worldwide wastewater treatment is not very successful most of the time. Wastewater is discharged without any form of treatment into the environment, spreading diseases to humans and damaging key ecosystems such as coral reefs and fisheries. Dirty water is a key factor in the rise of deoxygenated dead zones that have been emerging in the seas and oceans across the globe. This is becoming increasingly a global problem as urban populations are projected to nearly double in 40 years from current 3.4 billion to over 6 billion people. But already most cities lack adequate wastewater management due to the aging, absence or inadequate sewage infrastructure. According to the 4th World Water Development Report, presently only 20% of global produced wastewater receives proper treatment. Treatment capacity typically depends on the income level of the country. Thus, treatment capacity is 70% of the generated wastewater in high-income countries compared to only 8% in low-income countries. Environmental conditions arising from inadequate or non-existing wastewater management pose significant threats to human health, well-being and economic activity. The Millennium Ecosystem Assessment Report reported that 60% of global ecosystems Services on which many social and economic activities depend are being degraded or used unsustainably, and highlighted the inextricable links between ecosystem integrity and human health and well-being. Wastewater can be utilized in agriculture by the integrated application of measures as wastewater treatment, crop selection and restriction, wastewater irrigation techniques, etc. However, the criteria for wastewater treatment intended for reuse in irrigation differ considerably. While it is intended that diseases causing viruses are removed to the maximum extent possible, some of the biodegradable organic matter and nutrients available in the raw wastewater need to be maintained in many arid and semi-arid countries facing water shortages due to lack of proper precipitation. Wastewater is an important source of irrigation water. The increasing demands for both food and water by the growing population requires the agricultural sector to increase food production with lesser use of natural water resources. The use of treated wastewater for irrigation is the solution, but it requires a lot of expertise. Conclusion: reuse of wastewater can help to maximize the use of limited water resources. It can help to contribute in national development. Even though there is environmental damage caused by reuse of wastewater, it should be minimized as much as possible. Steps should be taken to minimize the health risks associated with reuse of wastewater so that the community at large and the economy do not face problems. Collaborations between users, authorities, and the public is needed. Exchange of ideas, experiences, strategies between the planners and the beneficiaries is of utmost importance. Government support and encouragement is needed at all levels. Thank you.